All right, we learned today about vsper, valence shell electron pair repulsion theory, as it pertains to defining the molecular shape. Now again, why do we care about vsper? Well, we need to understand the molecular shape of a molecule because being a molecule's shape helps define what the properties of the material are on a macro scale. When I mean macro, is something that we observe. So for example, why does water boil at 100 degrees C, whereas hydrogen sulfide doesn't? Or why does water boil at 100 degrees C and methanol, CH3OH, which is heavier than water, boils at a less temperature than water? It's all based on molecular shape and the polarity of the molecule. Now, vsper is important to help us understand the molecular shape, and it is also important to help us understand if the molecule is polar or not. Now recall, we know how to calculate polar bonds, but that doesn't necessarily mean we know how to calculate or determine whether or not a molecule is polar. And polar molecules behave differently than nonpolar molecules as far as properties, melting point, boiling point, solubility, things like that. So we need to understand how to determine the molecular shape, and we're going to use vsper rules to help us define that. So here are quickly the rules. Polar molecules have polar covalent bonds and asymmetry molecule shape as defined by vsper. In the vsper approach or model, lone pair electrons and bonded pair electrons on a central atom affect the shape of a molecule differently. And by applying vsper rules, we can now determine what the shape of a molecule is around a central atom. All right? We are going to use bonded pairs and lone pairs around a central atom to determine what the molecular shape is. Now, I provided you a vsper chart in class today, but let's quickly look at this one here, which is a little colorful and a little bit different than your one that I gave you in class. On the top of the chart, what you're looking at here are the number of lone pair electrons connected to the central atom, and I'll talk about that in a second. And on the left-hand side here are the number of things connected to the central atom. And we are defining things as atoms and lone pair electrons. So anything that's bonded to the central atom through a physical bond or attached to the central atom as in a lone pair of electrons are going to be things that are attached or connected to the central atom. So let's see how this works. So we have the total number of things attached to our central atom, and then we have a column here that defines only the things or the attachments that are lone pairs. So the difference in these two numbers is going to help us define what the molecular structure is. So let's see how this works. Let's say a molecule has two areas of electron density areas. In other words, there are either a electron pair, a lone pair of electrons, or a bond. A bond or an electron pair is considered to be an electron dense area. So if we have two of those and no lone pairs, we're going to say that the electron pair geometry is linear. Right, so our molecular geometry of our molecule around the central atom is going to be linear. If we have three things connected to the central atom, three things again being a physical bond of another element attached to it, or another atom, and a electron-rich area of a lone pair, if we have three things and no lone pairs, right, so the three things are all physically atoms, then we are going to say that the unit is trigonal planar. If one of these dense areas, electron dense areas, is a lone pair, we're going to say that the molecule has a bent shape, right? You're only looking at the shape of the physical atoms in the molecule, not the shape of the whole thing. So the molecular shape is bent. Yes, there is a lone pair here that still gives us that illusion, or it still has the shape of that trigonal planar, but these do not go into the what we're calling bent shape. If we have four things connected to a central atom, such as carbon, carbon has 4 spots where we can connect something to it, and none of them are lone pairs, they're all individual atoms around each one of the 4 spots, we're going to call that tetrahedral. And you guys made some of these in class today. If one of these locations is a lone pair, it's called trigonal pyramidal, or trigonal pyramidal, right? So that's what that. If 2 of those, like water, it's going to be bent. And then so on and so forth, right? You have 5 areas, you have trigonal bipyramidal. In other words, it's 2 trigonal planars on top of each other. Sawhorse, T-shaped, linear, depending on the number of lone pair electrons that are also attached to the central atom. So by using this chart, number of things that are attached to the central atom or bonded to the central atom, either a lone pair or an atom, and then subtract away or look at the number that are specifically lone pairs, you should be able to determine now what the structure of your molecule is. Right? So let's see how this really works. We must draw the Lewis structure properly. Then we determine what the central atom is. Count the things that are attached to the central atom. Atoms that are attached count as a thing, and lone pairs count as a thing. Anything that has a double or a triple bond is only counted once. We're only looking at things that are attached, not the number of bonds. So things, atoms and lone pairs. From the total things attached, electron-dense regions, count the number that are lone pair electrons. Then we use the chart to determine the actual shape using the total count and the lone pair count as criteria. Fairly straightforward. The key is that you must be able to draw a molecular Lewis structure properly. So if you struggle with that still, you have to master that skill in order for all these other ones to work. Okay, let's do some examples together. On the one on the left here, I've given you CO2, and I've already pre-drawn the correct Lewis structure. So let's count how many things are attached to the central atom. Our central atom in this case is going to be our carbon. So how many things do we have attached to it? We have 1 and we have 2. So we have 2 things attached to it. And how many lone pairs do we have? We have 0. We don't have any lone pairs on the central atom. We have bonded pairs, but we have no lone pairs. Remember, lone pairs are the 2 dots, right? So we go down to our number of electron-dense areas. We have 1, 2, 1, 2. Electron pair geometry is linear. We have no lone pairs, so our shape of this is going to be linear. So we would write here linear. Let's look at CH4 or methane. I've drawn the correct Lewis structure here. So let's count how many things around the central atom. We have 1, 2, 3, 4. All of them are bonded, so there's no lone pair, right? So now we have to look at our chart here. We go down 2, 3, 4. Here's my 4. We have no lone pair, so we go over to the no lone pair, and we see that that particular vsper shape is tetrahedral. I'm just going to write tetrahedral. That's an H. And you can see here what that shape looks like, and I think you made some of that today in class. Let's go down to our ammonia, or NH3, nitrogen trihydride, for those of you keeping track in the covalent naming system. So we got, let's see how many things we've got here. We've got a nitrogen is my central atom, and we have 1, 2, 3, 4 things attached. Remember, bonds are considered things, elements, atoms, and lone pairs. So we have 1, 2, 3, 4, and we have one of those is a lone pair. So now we go over to our chart here, 2, 3, 4. We are in 4 things attached to the central atom. We go over here and we see there's one lone pair, so that's trigonal pyramidal. So we put trigonal pyramidal. I'm just going to write T and M here. All right. And our last one is H2O, and I've drawn the structure here, and I've showed you before that that's probably not the best structure, but let's see how the vsper rules make it tell us what the structure is, right? So we have how many things are attached to the central atom? My central atom is oxygen. I have 1, 2 things attached, 3 things attached, 4 things attached. So again, we have 4 things attached. So we have 2, 3, 4. How many of them are lone pairs? There are 2 lone pairs. So we look over to 2 lone pairs, 4, and we see that that's bent. And we know that from fact that we know that water is bent. We've talked about that in class, so we know that's bent, all right? So now what I'd like you to do real quick is to try it on your own here and quickly do this on a scrap piece of paper and then come back when you're ready and we'll talk about the answers. So stop the video now and then start it when you're ready. Stop it now. Okay, so I've given you the answers here real quick, so let's just quickly review them, right? You should have written HCN. You should have seen that the carbon atom is the central atom. There are no lone pairs on it. There are 2 things attached to it. So we go down to 2, no lone pairs, linear. So 2 things attached, none of them are lone pair. We did see a Cl4, carbon, tetrachloride, tetrahedral, sorry. 4 things are attached, 4 chlorines. None of the things on this carbon atom are lone pairs, so we have a 0. And if we go down to our chart, we go to 4, 0, tetrahedral. And the last one is trigonal planar, right? If you do the correct Lewis structure here, you should have 2 chlorine atoms attached to a carbon, which is then attached to an oxygen. Even though the oxygen is a double bond, we only count it once. So we have 1, 2, 3 things attached to the carbon. So we go down to our 3. There's no lone pair on the carbon, so it's trigonal planar. So if you got those, you're good to go. These are just some common shapes that you'll see when you do some of these molecules. You'll see linear, 2 atoms. Anytime that there's 2 atoms bonded together, it's always going to be linear. Sometimes when you have 3 atoms bonded together, you also will be linear. We have trigonal planar, bent or angular. Notice that the green dots here represent lone pairs of electrons. Tetrahedral, where all the sides are equal. Trigonal pyramid, 1 lone pair atop. Some trigonal bipairs, and octahedral. So I've given you the key down here. These are going to be mostly the typical shapes that you will run into as a high school science student. Okay, for homework tonight, what you're going to do is you're going to copy these things here and construct a table on your own. You're probably not enough room here to take a picture of it and do it. But you're going to look at the compound here in this column. Here's my column here. And you're going to draw the correct Lewis structure from it. From that, you're going to determine the number of things bonded to the central atom. Again, remember, things are bonded atoms and lone pair electrons. You're going to look at the number of lone pair electrons down the central atom. Use the chart I gave you to determine the molecular shape based on these 2 things that you get here, and then put that here. So you have 6 problems or 7 problems here to do. You make a table tonight or bring them in on a piece of paper tomorrow for credit. Giving you some examples of each type you should see here. And then the last one's a little bit of a trick, but not really. When you draw the Lewis structure for the NO3, remember it's -1, so that means we have to add electrons or add 1 electron to the total valence that comes in with each atom to get an even number, and then construct your Lewis structure based on that. All right, so that's the end of the assignment, and then we can go from there.